Alright, so what we're getting going on right now is power generation. So how do we actually generate power? And so far what we've done is just use a little chemical reaction inside a cell to produce power. But that doesn't really produce power on a large scale or continuously doing it. Once the chemical reaction runs out, you're basically done. So what we're going to work on here is what is called is really just AC power, and that stands for alternating current. That's the AC. Essentially, what this amounts to is what we were talking about a little bit in the last video with flux, where we change the flux through a coil and we get current. And as you do it, what it's going to happen is it's going to make current go in one direction and then the other direction, and that's where the alternating current comes in. It goes back and forth. And our basic goal here is to spin a coil, spin a coil of wires in a magnetic field. I'm just going to put B field. It's often just called that anyway. In a B field, and this changes the flux through it as it goes from parallel to perpendicular to anti-parallel and all like that. It will produce an EMF. So I'm just going to put EMF. I'm running out of room there, sorry. An electromotive force. Essentially, that's what's going to happen. And you can come up with different geometries. It can be as simple as just spinning it right next to a coil, but you want to get as much flux through there. And so a lot of times what you'll end up with is you'll end up with something that kind of looks like this, where you can make like a little north magnet here, the north end of a magnet, this north, and then over here you're going to do something kind of similar with the south end of a magnet. That line shouldn't have been there. And you'll put just below it, put another magnet face the other way. So of course there'd be a north over here and a south up here too, but we're more interested in just this little section of it, right? And so you have something that looks kind of like this. Sorry if it's not the greatest drawing. And then inside there, what you can do is put a coil. So maybe I'll make my coil in a different color. But essentially what I'm going to do is put a coil in here, like a loop of wire that's inside. I'll put little dotted lines for right there where you can't see it. But you'd have this coil, right, like right inside there. And then what you're going to do is have it attached to something here that spins it. Okay, and if you're thinking about the magnetic field in here, out of north and the south, what you mostly pretty much have is a magnetic field, pointing down like this all through that region. And this then spins in that magnetic field, a very uniform magnetic field, and the flux changes as it lines up with the magnetic field and when it goes perpendicular to the magnetic field. And so what you'll get, and then of course as it flips the other way, it'll reverse the direction. What you'll get is you will get a voltage produced from something like this. Here will be our little EMF, right? What you'll get, EMF as a function of time, is you'll get something that looks like this. Get yourself a nice sine wave, essentially, as the voltage goes up. As this goes through one orientation, drops down to 0, and as it turns such that there's no flux, so that it's perpendicular, and then as it goes and faces the other direction, and this will happen as your loop constantly is trying to undo what you're doing. So as you add flux through it one direction, it tries to create current, a voltage in one direction. As you flip it so it's got 0, it'll cut off. As you turn it for the other direction so that the coil's turned over, it tries to create current in the other direction to get rid of that flux, and so it just goes back and forth like that the whole time through. For this, what you end up with is you don't end up with a constant voltage. Like here, you don't get a constant voltage, but what you do is we have to talk in terms of some sort of average and maximums. And so, like from this graph, we can say the power. We had P equals VI before, and what we can do is do a different version here, where we can say the maximum power, right? The maximum power that you get, P max, is equal to maximum voltage times maximum current. All right, where that's V naught is a max and I naught is a max. I think I would have preferred to have written max or an M or something for them instead of the naughts, since the naughts are usually for initial and you don't know where in this cycle you're going to be when you first start or when you walk up to it. But we say they're treated as maximums, and so we've got that there, and that's just the way your data booklet has it. So P max equals V naught I naught, and that gives us that. We can also go through and do a little something with this. We can say that if that's the case, we can get just regular power average. Our average power is going to be one half I naught I max squared times R. And if you remember, we can make this into this equation. We can take V equals IR and replace V with IR, and so P equals I squared R. And so we can get our average from this. Again, that's maximum. And from there, we can say this is 1/2 V naught I naught, and then of course we can go then maybe I'll write it down here, that average power, because this is our final version you'll get actually in your data booklet, is 1/2 I max V max. And so that's what you'll get for average power, different than maximum power, but average power through this. Well, I probably should explain to you where the 1/2 comes from. That might help, huh? Sorry. Just going off without explaining that. Think of if we took this and instead of doing V versus T like this, we did I squared times R. So because of this squared, we'll get rid of our negatives, and we can actually end up with a graph that looks like this. All right, we'll move this sine graph up and out of the negatives, right? That's why we do that, so we don't end up with this. Because if you average this graph here, it averages to 0, right? You have as much above 0 as you do below 0, so this would average to 0. This averages to half the maximum. Half the maximum here is 0, like half, between them. Here, between the max and min, is just half of the total maximum, and that's why we get that half I naught squared R. Sorry, I forgot to draw that graph for you before I started, but it's this is the average right there. That's your average, okay? And that's half the max. 1/2 the max. Sorry, I ran out of room there. Half of the maximum, okay? So there's that one. Even though I kind of did it in a bad order. Now, we've got all this stuff, but we have to be able to talk about how does this compare to DC versions. So we can do a little bit of effective DC versions. Like what would be the analog to this in DC? If I had a DC direct current, which is what we're talking about, like you get from batteries, what would be the equivalent of that? So, and this is given, you get the DC equivalent, it's given by what is called the root mean square. And that's literally, it's called the RMS, and it's literally the square root of the mean of the square of your data value. So if you had just a list of numbers and you wanted to do this for, what you would do is go through, square all your numbers, take the average, and then take the square root. So it's the root of the mean of the square. And that's what that RMS is, and it's just shortened to root mean squared, or just RMS. For current, the RMS is I naught maximum, so maximum over square root of 2. And then similarly, the voltage, the root mean square voltage, is V maximum over square root of 2. And so these are the two equations that you'll be given. Now the only way I know how to derive these is with calculus. And I'm going to go ahead and do it now in case you ever want to know it at some point when you get to the calculus stuff like this. I'll just show it to you once. If you don't want to, you can feel free to just either go ahead and turn this video off because this will be the end of the video, or go ahead and skip on. Actually, I have one more. Let me give you one more equation before I do the calculus. Sorry, before I do the calculus for this, we can do, just in case you want to turn it off, V equals IR, and then we can do, from there, we can lead to V naught equals I naught R, so the maximums. And that basically then tells us here, our last little thing is that R is V max over I max, which also equals V RMS over I RMS, because the square roots would just cancel. So that's our last relationship. So now at this point, if you want to go ahead and skip, you can, because this, you can just turn the video off. If you want to see the calculus, go ahead and leave it on here. So let's think about this. How are we going to do this? So again, we have to square it. So let's start with the square. Let's start with V. So this will be our RMS. It'll be that squared. Okay, and when we get to the end, we'll take the square root. So the way you take the average, right? So we have to square it. This is our squared. We have to take the mean, and then we'll take the square root at the end. So let's go ahead, and this is it squared. Now let's take the mean. So essentially what you do to take the average of something is you add it all up, and then you divide by the total. So what we're going to do is divide by one whole period of the cycle. Remember, this is a graph that looks like this, so we're going to go through one whole period of it, right? One period, and it's a sine wave. It's a cycle, and then this is our summation in calculus. It's an infinite sum. We sum over, instead of discretely, and we're going to sum over one period. So from our start to one period through it, okay, one revolution of it. And this equation, of course, has an amplitude equal to, it's an amplitude. It's a cosine or sine graph. I think I drew a sine, but it can be sine or cosine. It's not going to make a difference. I did this out for a cosine. So if we wanted, we could shift our origin over, call that 0, and go back up to here and call that the period. Ignore that part there. Now it's a cosine graph. Cosine of omega t, that's our frequency, our angular frequency, dt. So this should look kind of familiar to you, at least from, this is how sines are. Oops, I didn't mean to put the square on there yet. So that would be our equation for our function here, our amplitude for voltage versus time. And then what we of course have to do, it's of the square of it, so we need to square this. So those get squared. So we square it, and now we're taking the mean. So this is our equation squared, this is our function squared. This is us, this here, this integral, and this little dt at the end here is adding it up through here. It's called integration. We're adding it up over a period, and then we're dividing by its value over one period, okay? So this is how you take an average of a function using calculus. V naught is a constant, so that can come out front. We don't have to add it up. We can just add up all the other numbers and then multiply by that total constant. Basically, this is a coefficient that's on every single term, so we can just take it out and ignore it from the sum. It's like factoring it out. And then we have just the integral of a cosine squared. That's kind of difficult, so you just go to your power reduction trig identity, all right, the power reduction trig identity that allows us to replace a cosine squared with a 1 plus 2 times theta, so 1 plus, oops, that was supposed to be a C, 1 plus the cosine of 2 times theta, which is omega t in this case, all over 2. You can look up that trig identity of cosine squared turning into that. All of that summed up, dt. Then what we have to do is something called u substitution, where we can bring this 2 out front, so that's a constant, I can put that out here, and I can say u substitution. I'm going to say u because I have this 2 omega t in here. I don't want to mess with, so I'm going to say u equals 2 omega t, and when you get into calculus, if you haven't yet, I'm telling you, you'll understand all this. Right now I'm just going to show it to you. Du is, take the derivative, is 2 omega and then dt, so the derivative of infinitesimal derivative with respect to time of both times, so du dt, and then I can substitute that in over here. Maybe need to move down just a little bit, give myself a little more room, so ignore that. So right here we substitute this. I have v naught squared over 2 times the period, still have my integral here, and now what I have is this is going to become cosine of u, so I'm going to replace 2 omega t with u, so this becomes 1, well actually I'm sorry, I'm going to split this, so I'm going to do the integral of this and the integral of that separately, so this will be just the integral of 1 times dt, so dt from 0 to t, and then I'm going to do plus this second part, this is the thing I was doing u substitution on, plus my integral here, 2 omega t becomes u, this is cosine u now, and dt, if we look at this, dt equals du over 2 omega, right? dt equals du over 2 omega. So this becomes du with an over 2 omega here. And 2 omega is a constant, so that's not going to matter. Now if we plug in 0 for t here, we get 0. And then if we plug in period, I'm changing my limits here, right? Plug in the period here, we get 2 omega t instead of just t, 2 omega t, right? Because this was going to substitute in for this t here, so we have to substitute out 2 omega t. And now we have these two integrals. So v naught squared over 2t. This one's really easy if you've done integration before. It's just going to give you t evaluated from 0 to the period. The second one, well, the integral of cosine, right? We're going to have our 1 over 2 omega here. That's a little constant in front of that one. We're going to have that, and then we're going to have times the integral of cosine is just sine. Real easy to do, sine of u, because derivative of sine is cosine, and so the integral of cosine is sine, and this is evaluated from 0 to 2 omega t. Okay, and now we've done that. That's our integration, that's our sum of it all. So this part from 0 to t, you plug in this number and then subtract this number plugged in. So we've got our v naught squared over 2t times, this is t minus 0, so just t, right? And then plus, what do we have? We've got a sine of 2 omega times the period. Well, if you think about this, let's look over here. This is the sine of 2 omega times the period. Well, what's omega? Omega is 2 pi f times the period. F is 1 over the period, so period times frequency just is 1, so this is 4 pi. So this is just the sine of 4 pi. And what's the sine of 4 pi? Well, go around your unit circle twice, right? 2 pi, 4 pi, and when you're there, it's 0 for the sine. So this is 0. The other one is the sine of 0. When we plug in 0, sine of 0 is just, well, you just stay right there. It's 0 as well. So this whole term right here is a 1 over 2 omega times 0 minus 0. It's just, the whole thing is just 0, right? And so what we end up with is just this right here. I'm going to bring this down. We have the RMS squared is equal to, And now these t's will cancel, and we have v naught squared over 2. But these are both squared, and so now remember, it's the square root of the mean of the squared. So again, we squared everything. We took the mean of it. That was averaging it all out. That was all of this. This is our average of the mean. I'm sorry, this is our average of the square, and now we have to take the square root of it. So you take the square root, and you get VRMS equals V naught over the square root of 2. And that's exactly what equation I gave you up there. If you didn't understand it, if you watched this and you didn't understand it because you haven't done integration very much yet, just hold on to this video, come back and watch it once you've done integration, and it'll make more sense to you. But there it is. There's that square root of 2. You can go back and instead draw this same graph for current versus time and replace all these V's with I's, and it'll work out exactly the same way. Do the exact same math, and you'll get over that square root of 2 for both of them. So you get both of those equations. Okay? So anyway, I hope I didn't scare you off too much with the calculus. And like I said, you don't have to know this calculus. I just thought I'd put it in there for completeness. Feel free to skip that part at the end of the video when you're studying, getting ready for the exam. But if it interests you, there it is. Okay? I think that's pretty much everything for this video.